Okay, this is Unit 1 notes of piecewise functions, evaluating and graphing notes. Here we are going to look at the notation of a piecewise functions and then how to evaluate if we're given a formula. So looking at the first here is this notation. Okay, so this is the notation of a piecewise function. Our piecewise function is broken apart into different expressions. So in this example, we have three expressions. We have the first one that falls within the first interval, the second one with the second interval, and then the third one with the third interval. When I say expression, when I say expression, that means it is without an equal sign. Without an equal sign. And when I say interval, think about domain. Okay, so we have a piece of a function, an expression, within a specific domain. So if we're looking at these examples here, starting at the first one, in this piecewise function, we have two expressions. We have x plus 4 on the restriction x is less than 0, and we have negative x squared plus 4 where x is greater than or equal to 0. So we have two expressions here. If we look at this function, notice that it is two pieces of different graphs. So in that first one, we have a linear function that goes with our x plus 4, and then we have a separate piece of our quadratic function, that negative x squared plus 4. So we know that a linear function looks like a line. So here we see the whole line, so it doesn't look like we have a piece of it. But we also know that a negative quadratic is an upside down U shape. So notice we don't see that full U shape there. It would technically look like this. Okay? But if we look at our restriction says only the x's that are greater than or equal to 0. That's why we only have this piece of our quadratic. Okay. And then looking at this one, we again have two expressions. We have a constant function on this domain, and we have a linear function on this domain. Okay. Remember, when you see just a number, this is a constant function. A constant function always gives a horizontal line. So our constant function in this case is this horizontal line here. And then we can tell on the other side that this is our linear piece. Now looking at example 1, we need to break down this piecewise function so we're able to evaluate it correctly. So before I do that, I'm going to change all these P's to F's because that was a typo. And then what I'm going to do is I'm going to break down my piecewise function. So my piecewise function here has two expressions. I have a linear expression on this domain, and I have a quadratic expression on this domain. So in order to figure out the answers to these ones, I have to remember that if that number is in the parentheses, that is an x value. So I need to see where those x values fit on which domain. So for this problem, I'm going to refer to the pink domain and the green domain. Okay, so you can see the difference. So for this one, we have f of 1. So I need to see where 1 falls on either the pink or the green. So for pink, it's all the values that are between 0 and 5. 1 is between 0 and 5. So that means we are going to evaluate f of 1 using that pink expression. Okay, so in this case, it's 3x plus 5. But instead of x, I'm going to put 1. So 3 times 1 plus 5 This gives me 8, which is the point 1, comma 8. Okay. Now I'm going to look at the 5. So I need to see where 5 fits on the domain. Well, the first one is 0 to 5, including that 5. So we know it's going to fit on the pink. But let's just check the green just to be sure. This says x is greater than 5, but not included. So 5 is not greater than 5. Okay? But 5 is equal to 5. So again, we're going to evaluate this on the pink expression. So we have 3x plus 5. Instead of x, I'm going to put 5. 3 times 5 plus 5, which I get 20. So I have the point 5, comma 20. Okay. Now I have f of 10. So looking at my domains, my first one is 0 to 5. Well, 10 is not between 0 and 5, so that one doesn't work. Now I look at the next one. Is 10 bigger than 5? Well, 10 is greater than 5, so I'm going to be using the green expression on this one. So I have x squared minus 3. Instead of x, I'm going to put 10. So 10 squared minus 3. That gives me 97. So I have the point 10, comma 97. Now I'm going to look at the last one, f of negative 6. So I need to see where negative 6 will fit on the domain. So negative 6 is not between 0 and 5, so that one doesn't work. But negative 6 is also not greater than 5, so that one doesn't work. So if it doesn't fit in either the domains, then we say that this answer does not exist. So the x value of negative 6 does not exist on the function given with either expression. Okay, and we're going to do the same thing for example 2. So in example 2, instead of 2 expressions, we now have 3 expressions. We have that constant 8, and then we have a linear function x plus 10, and then we have another linear function 2x minus 6. So we have to look at each one and see where it falls on which domain. So for f of 0, we have to see where 0 belongs on this domain. So this first one says x is less than negative 4. So we would say 0 less than negative 4. Well, that's not true. 0 is not less than negative 4. And then looking at the blue, 0 is greater than or equal to 3. Well, that's not true either. So that means our 0 must fit between the negative 4 and 3, which it does. So this is our pink one. Okay, so I have x plus 10, but instead of x, I'm going to write 0 plus 10. That gives me 10, which is the point 0, comma 10. Okay. Now I look at 3. So where does 3 fit on this domain? So to me, it looks like it's either going to be the pink or the blue one. Okay. But notice on the pink, this one does not include 3, but on the blue, it does include 3. So that means this f of 3 is going to be on the blue expression. So I have 2x minus 6 is equal to 2 times 3 minus 6, which equals 0. So I have the point 3, comma 0. Okay, now I'm looking at negative 100. Negative 100 is not greater than 3. It's not between negative 4 and 3, but it is less than negative 4. So notice, since this is a constant function, that green expression, we have nothing to plug in. So no matter what value of x that is less than negative 4, the answer is always 8. So I just write 8. But if I was writing the point, it would be negative 100, comma 8. Lastly, we have f of 100, so we need to find where this 100 fits on this domain. Well, 100 is not less than negative 4, so it's not that one. 100 is not between negative 4 and 3, so it's not that one. But 100 is greater than or equal to 3, so it's going to be the blue expression. So I have 2x minus 6 is equal to 2 times 100 minus 6, which is equal to 194, or the point 100, 194. Okay. Notice in my answers, I had part B and part D both use the blue expression. So that tells us that we can reuse the same expression as long as our x value falls within that domain. Okay. Example 3 says graph the given piecewise function. So notice off to the right, we have a piecewise function that has 3 expressions. We have a quadratic, a constant, and a linear. So we are going to have to plot each of these separately in order to create our overall piecewise function. So in order to do that, what I'm going to do is I'm first going to create XY tables for each of these functions. So starting with x squared, so our quadratic, so we know that x squared is quadratic, and it's going to look like that U shape. I have a XY table for my x squared, and notice my domain says x is less than or equal to 0. So I'm going to plug in 0, and I'm going to plug in numbers that are less than 0, so -1, -2. And then I'm plugging them into my x squared. So I have 0 squared, which is 0, -1 squared, which is 1, and -2 squared, which is 4. Okay, so I now can plot those points, 0, 0, -1, 0, or sorry, -1, 1, and -2, 4. So 0, 0, -1, 1, and -2, 4, which is going to be off the graph and off to the left. Okay, remember my domain was that x is less than or equal to 0, which means I'm going to have a closed dot on the 0, and then my function is going to go up to infinity. Okay, so that's my first one. Now I'm creating an XY table for my constant function of 4. So it says from 0 to 3 is my restriction. So I'm going to write 0, 1, 2, 3. But on my 0 and my 3, I'm going to go ahead and highlight that 0 and 3 because it's not included, meaning I'm going to have open circles there. And now I'm plugging them in to get my y values. But since the function is constant, we know all my y values are going to be 4. So I'm going to get, for 4, constant, and it's going to look like a horizontal line. Okay, so plotting those points, 0, 4, 1, 4, 2, 4, 3, 4. Okay, on 0 and 3, they are open circles. So open circle, connect them. Okay. Now I have my last XY table for my x plus 1. So my linear, x plus 1 is linear, and it's a positive linear, so I know it's going to go in the positive direction. So here it says x is greater than or equal to 3. So I'm going to plug in 3, and then I'm going to plug in 4. So if I plug in 3, I get 4. If I plug in 4, I get 5. So I'm going to plot those points. So I have 3, 4. Notice right here, it now covers the same point as my constant function, 3, 4, which means this is now a closed dot. Okay. Then I'm going to plot my point 4, 5, and I know that my function is going to infinity and it's linear, so it's going to have an arrow going up. So everything that I just plotted, this entire thing represents the piecewise function given to the right. Okay, but we had to break it down to create each of the pieces separately in order to graph them. Okay, Number 4, number 5, we have to look at the graph in order to evaluate our problem here. So looking at the first one, it says find f of -1. Well, -1 is my x's, so I'm going to go -1 on my x's, which is right here. And notice I already crossed a point on my function, which is 0 for the y's. And since it is a closed dot, it is included. So I am going to write 0 or the point -1, comma 0. Now I need to find f of 3. So I'm going to find 3 on my x's, so right here. And notice I can go up and I can go down to hit my function. However, I'm only going to go up because that's the one that is a closed dot, which means it's included. So my answer here is 4. Or I would write this as 3, comma 4. Okay, now f of 8, we're going to find 8 on the x's, and notice I can go down to hit the graph, and I hit it at the constant function -4, and since it's a solid line, it is included, so -4, or 8, comma -4. Now on these two, it says f of x is equal to a number. That number is y, right here. This is y. So I'm going to find 2 on the y's, which is right here, and I can only go right to meet my graph at x equals 1. So this is x equals 1 or the point 1, comma 2. Same with my 6. I'm going to find 6 on my y's. So that's right here. And I can only go left to hit my function at a closed dot at -4. So x equals -4, or in other words, -4, comma 6. Last example here, we have f of -1. So I'm going to find -1 on the x's right here. Okay. And then notice I can only go down and I meet it at a solid line at y equals -2. So -2 or the point -1, -2. Okay, now looking at -3. -3 is right here on the x's. I can only go down and I hit my graph at a solid line at -8. So I have -8, which is -3, comma -8. Okay, and then +8 on the x's is right here. I can only meet it in one direction, that is up on a solid line when y is equal to 3. So I have 3, or in other words, 8, comma 3. And then remember, for these last ones, if we see f of x equals, then we are finding that value on the y's. So I'm finding 1 on the y's, which is right here. Okay, and notice I don't need to go anywhere because it already hits that x value at 0. Okay, but let's double check that we don't have any extra ones. So right here at y is equal to 1, I'm now looking left or right to see if I will hit my graph. Well, I can go right, and I can hit that graph at about 1.4, 1.5. So I'm going to have an approximation of x approximately equals 1.4, which means I have 2 points here, 0, comma 1, and 1.4, comma 1. Same thing for my -5. I have to verify that how many x values can hit that y value. So -5 is right here. Notice I can go left and I can hit that at -2 at a solid line, or I can go right and I hit it at about 2.9, also on a solid line, which means they are both included. So I have x is equal to -2 and x is approximately 2.9. So I have the points -2, -5, and 2.9, -5.